Well, it's great to be here today, and so I would like it, probably going to be involved in some of this. It's not going to be just a lecture. So get out a pencil and a paper if you would, get some things so that we can talk about hydrogeology. I don't know how familiar you are with hydrogeology. It's probably one of the greatest and one of the most interesting things as far as facts once you get, quote, into it, because you have to go underground to, quote, get into it. It's not right on the surface. So hydrogeology is going to talk about, as far as your definition, hydrogeology is, of course, hydro is water, geology is earth. And so what we're going to talk about today is the movement of water inside the earth. Now that, when Heavenly Father and our Savior actually created this earth, there was also a lot of planning regarding to store water somewhere that would be usable in a different form, in a different shape than we're typically used to. So let me just go back here. Water everywhere, not a drop to drink. We have oceans that constitute 90-something, 80-something, 90% of our water. And so that's not really available for all of the different uses that we have, so we have to have other sources. So what happens is we go to underground reservoirs and we also have surface water. Here's some terms I want you to remember. We'll talk about that. I want you to remember about cone of depression, water-bearing formations, and drawdown. What that does, that will give you some real insight as far as when you're working with underground or with water, which we call groundwater. There's two main sources of water. You have surface water, and you're all familiar with that because you've all been around with lakes and rivers and so forth. Then as we go down into the Earth's surface, we have the wonderful opportunity to work with groundwater. Groundwater is located under the ground, obviously, with large aquifers. You need to be aware of what an aquifer is. Basically, and the only way we extract this water typically is by drilling wells into the aquifer and extracting it through a pump. And so that's the other issue. What happens, people, is you have a top layer, for instance, then you have your actual aquifer, and then of course you have maybe a bedrock or something, what they would call a confining layer. A confining layer keeps the water in a certain place. If it's not confining, that water is going to move wherever it wants to. It doesn't move very rapidly. It can take hundreds of years to move a few miles. But this water is stored in the earth in an aquifer, and it does move based on the porosity. What's the porosity? The porosity is how big are the openings of the fractures that the water is stored in. If you have large openings, then obviously you're going to have that water is going to be able to move rapidly, comparatively speaking. If it's real fine, or if you have clays, that's a confining layer. It cannot move through that formation, or it moves very slowly. So these are the things you have to be aware of as you start. What happened in environmental engineering is you have a contamination source. So maybe if you have a plant over here and a plant over here, and all of a sudden this groundwater is contaminated, you have to go and do the forensic type and say, who is the polluter? Well, you have to do that. You have to know a lot about the formation. You have to know about the groundwater. You have to know which way it's going to flow or not going to flow. And then you have to look at the contaminant source. Is it going to come from this plant or this plant? A lot of these things, which is really interesting, because then you get into the legal aspect of it. You ever heard of EPA? Okay, guess what? Who gets to pay? The deep pockets. They go for the people who have the money. Because if you have the money, then you can do the remedial action. You can go in there and clean up the source. You can do the remediation to get that source back out of the groundwater, get it clean again, and then go forward. So let's look at this as far as groundwater. What happens is you have the hydrogeological cycle. Basically, we never lose water, people. It stays here. But what happens is it transforms from one source to another source, really just kind of something that's going to confine it or store it. So what happens is we're all familiar with the rain and the snow and the precipitation. It comes down through here, and then the infiltration, which you do in Hawaii have probably one of the greatest water sources that there is as far as clean water, usable water, is right here in Hawaii. Why? Because this filtration is made up of volcanic rock, and so as this water goes down through this formation, remember that formation, and it trickles down through here, then it is cleansed and ready to go. So it's rainwater. So you have a great source anyway, you have a filtration system, and now you have this water stored here, and all you have to do is extract it. So that's something that's really, really a great situation where you're living. Number one, the water source is fantastic as far as purity. It's available. You have large quantities of it. And so that makes it nice. Who knows what, let's talk about some type of movement of water where it's actually visibly seen and it starts flowing. What's that called? It's artesian. You ever heard of an artesian well or artesian source? What happens in a situation like that is, if you have groundwater stored right here, and you have an opening that sits over here, here's a stream, you've seen it come down. What happens is, here's an underground source of water. If there's a little conduit, this water, here's your land surface, this water then is stored here. Well, there's enough pressure, and this is a low enough point, these are all points, this water begins to flow. Hits an open channel, and all of a sudden you have this little stream that you didn't have before. Now, if you pump this too much and you drop that water level because of pumping down to here, that stream will dry up. And so that artesian head that you used to have is no longer available to you because you've dried this source up through the pumping or drought, maybe it doesn't rain anymore. This little aquifer, again, your aquifer sitting here, does not have, quote, the recharge. What's a recharge? That's the amount of water coming into your formation. So if you don't have enough water coming into your formation and you're extracting at a certain rate, then pretty soon you're going to dry up that aquifer and it's no longer available for use. So that's what you have to do. When you start looking at hydrogeology, you've got to say, okay, where am I? What do I need? What does I need the water source? How much? And so forth. So let's go forward. But that's a hydrogeological cycle. It lets you see how water really moves from one point to the other, even though we don't lose it. 2 M's blessed me and continue to bless all my life. What were the 2 M's? Boy, I better remember that. 3 M's. Great job. Great job. Boy, don't ever tell me the other part of it. Okay, 2 M's. One of them was that you go on usually when you're 19, and now the girls do. Okay, we went on a mission. First of all, a mission. Academic before I went on my mission was pretty bad. They told me don't come back. Little start probation, put on academic suspension, so I went on a mission. Thank goodness I had a choice to go there. But anyway, so I went on a mission, and then I came back and I understood what I wanted, number one, and number two, and how to get there. Before, I don't know if I wanted it, and number two, I really didn't know how to get there. So this blessed me tremendously because then I came back, everything went great, got back in, did the dean's, I'm not saying that's the way, I'm saying it because you can be successful. Came back on the dean's list, came back on the master's, went summa cum laude, and went that way. So you can do it even if you have issues before. The second thing, the second M was a master's in environmental engineering. I went to the plant that I worked for 36 and a half years when I was getting my master's, which was quite a few years ago, probably back in the 1990s. Anyway, came back and gave a presentation. I was in the process of working on this, and I came back and gave a presentation to the plant manager where we worked, and it had to do with water. We worked at a coal-fired power plant. If you're going to work at a coal-fired power plant, you're going to generate electricity. Everybody that turns on the light switch, what do you think is going to happen? What do you expect to happen when you turn that switch? The light goes on. It isn't magic, people. Somewhere down the line, a long, long, long ways away, there's a big generator that's turning, and that generating electricity. And that's why when you turn on the light switch, you actually have that light come on. So it isn't magic. There's work going on way down here in order for that electricity to be here today. So how does that work? Anyway, I gave this presentation. As soon as I gave the presentation, the manager said, hey, look, I want you to take all of our water. I know the private issues, the legal issues, the production issues. I want you to take all these things and take over. That was a huge learning curve because even though in class we were learning things about hydrogeology and contaminations and wells and all that, we still had to make a huge transition. So this is what happened. Okay, people, this is what happens in a power plant, so be aware of this. This is what you call your boiler. What happens is you take water, and we're taking water at about 7,000 gallons a minute. Somebody get a calculator out and give me how many gallons that is in a year, if you would. We're taking 7,000 gallons a minute. We're heating this water up to a point where it's pure steam. You can't have any droplets in steam if you're going to actually expose those to a big turbine. That turbine will blow up. As soon as the water particles hit those blades, that turbine would come apart. So it has to be pure steam, and you also want it as far as the purity. The purity has to be perfect because you can't plate material out on your turbine. Otherwise, you're going to get a deposit. That turbine's going to have issues. It's not balanced anymore. That thing's going to go again. So when you start generating electricity at 7,000 gallons a minute, you've got to have a pure water. This then in turn comes back as a steam, turns this turbine at 3,600 RPM. What's an RPM? What is it? Revolutions per minute. So every minute this thing is turned 3,600 times. Why is it turning? Because it's turning a generator. What's that generator doing? It's going down that big transmission line that you guys have seen throughout your life. And that's why when it does, that's why your lights come on. So that isn't magic. This is all that's happening way, way, way somewhere. What happens too is you have to realize is we're using 7,000 gallons a minute here. You have cooling towers. Why would you have cooling towers? Once this steam hits this turbine, you've got to take all the heat out of it and put it back into a liquid. You can't pump steam. So what you're going to do is you're going to take all this liquid that you have, take it back down to a form that you can pump it, which is water. You have to extract the heat, but you want to do it economically. Every time you extract some heat, you want to put it back into your system because it took heat for your system to function. So now you have to take this heat and you have to put it back in your system as much as you can, but the cooling towers then are taking the heat off, and you're going to lose about 6,000, probably about 6,000, about 84%, 86% of your water goes out the cooling towers. You'll never see it again. So all the time you're bringing this 7,000 gallons in 24/7, 365 days a week. So would anybody come up with a total? How many billion gallons is that? 3,600,000. That's a lot of water, people. If you have any idea how much water is consumed here on this island, we could probably supply that, no problem at all. So that's a lot of water. Okay, how did I get involved in this? Like I said, I gave a presentation in the plant where we worked. In 1979, we had 5 wells in one well field, and each of those wells produced about 1,000 GPM. Also at the same time, there was another well field that had 5 wells, and each of those produced about 1,500 gallons a minute. So there was a little bit different. This one is 20 miles away. This was more like 2 or 3 or 5 miles away. What happened over time was, can I erase this for a minute? Yep. Okay, thanks. What happens, people, is you start pumping 7,000 gallons a minute out of an aquifer. And like I said, remember these terms. Here's your aquifer. You're pumping out 7,000 gallons a minute. This particular aquifer, remember, in order for water to get through here, it's got to come through this formation. And it's going to come by gravity, because what happens is you create a void when you pump. So the void has to be filled. Well, how is it filled? Gravity then starts putting water back in as you're pumping water out. If you're not having enough recharge coming into your aquifer that was at this level starts to drop and drop. So your wells then, that used to be pumping water from this level, now have to pump from this level. So what happened was, these 5 wells up here had a capacity of 5,000 gallons a minute, right? And then what happened was, is we pumped this aquifer, and this is what we called overdraft. Overdraft is you're pumping out more water than you're putting in. So now all of a sudden these wells back in 1992 started dropping off, and they gave me that responsibility, remember? So I started graphing production. The power plant has to have at least 3,500 gallons a minute coming out of this well field. We were going to hit that at a certain point. So I went to management, I said, hey, look, you guys, you better put another well or two. We're going to come to here, and when you start actually no longer producing the capacity that your big power plants used to or are capable of, you lose millions of dollars. It's not just a little thing. These plants produce millions of dollars a day. So when if you start curtailing generation and you no longer have generation, then pretty soon that's a costly situation. You can't put a well in a well field in a day or two. It takes years. You got to buy the land, you got to go over there, you got to develop, you got to drill your wells, you got to put a pipeline in, you got to put a power line in. All these things take time, so you got to project out. You got to say, okay, look, I need this then. So I said, you guys need it, and you need it right away. Let's start. So we started. We put in 2 new wells. That kicked us back up to 5,000 gallons for that well field because we put in 2 wells. Now we have 7. We went on a little bit longer and ended up doing more wells. So we drilled 3 more wells. And the great thing was I was blessed tremendously because no one knew it, because every time we kicked in those wells, we kicked in 2. That was 1992. In 1994, it took us 2 years to do it. We did the highest capacity factor. What's a capacity factor? That means of your generation. We did 94% capacity factor. We were used to be running down in the 60s or so. So if we wouldn't have had those 2 extra wells at that time, we would have been curtailed in generation, losing millions of dollars. But since we were able to put those 2 new wells in when we were supposed to, then all of a sudden we had no issue. There was no hiccups, no one knew anything that we did it, and we came right back and everybody was fine. So that's what, like I said, a total blessing. We drilled 3 new wells that way. So when you took over the responsibility, you never drilled wells before in your life, you had no idea what was going on. Then you started looking at the particular, as far as the hydrogeology. Here's your land. Here's that artesian spring we talked about. And here's the actual aquifer. So you have to start going into wells and water. What do you have to know when you drill a well? Do you have any idea? What you have to know, people, is you have to know your geological formations. You have to say, okay, if I drill 30 feet, 40 feet, these wells are 1,200 feet deep. They produce 1,500, 1,800 gallons a minute. So before you start drilling a well, you have to know what the formation is. You know, how am I going to drill 50 feet and be fine, or 100 feet, or 2 or 3, or so forth? What you do then is you start drilling, and you look at different wells around the whole area. What should I expect in this area? So you start looking at different wells, and what they do when they drill a well, they have drilling logs. Those drilling logs show every foot that they went down through. They also define what the material that they hit as they went through there. So you go to your neighbor, you look at his drilling logs, and you say, okay, I know about what I'm going to do. So anyway, so for instance, where we are, there's a clay formation here. Here's your static water level. This is about 350 feet. Then you have what they call a kaibab formation where we are. It's fractured limestone. Well, the reason fractured limestone is so good is why? Fractured limestone is the key. What do we say about water being able to move or be stored in a formation?
Fractured limestone is the worst.
Very good. So fractured limestone is like this. Has a real great capacity to store, and secondly, has a great capacity to transmit. Remember, if you're pulling out too much this way and not enough coming in this way, it doesn't work as well. Fractured limestone is super because you can store all kinds of water and you can transmit or get out a lot of water. So that was great. Coconino formation is different. It's a very, very high-packed sandstone. So water getting through that and coming out is a lot tougher situation. But you need that formation because it is a water-bearing formation. So now you're going to go to here, to here, to here. The supai, what happens when you drill down to here, probably about 1,200 feet, you hit what they call a supai. The supai is strictly salt. You don't want to go into the supai and destroy your well. So as your well driller is drilling, he hits the supai because he has actually conductivity meter, and he knows when he hits that, all of a sudden, that meter goes off. So he knows he's hit the supai. They back off, we do the well. You have to build, when you construct a pump, or construct a well, here again, this is your screening. That's an open part, but it's a metal screen so that the water can come through. It's very, very open, but it also has slots and different things. Now this water is able to come through here. This is solid. When we put a well in at one of these wells, the water was so aggressive, if you put in great, if you put in great big 16-inch carbon steel, then in 2 years you can take it and throw it away because that water would eat that up in 2 years. Your well casing was gone. So what we had to do is we had to go to stainless steel. When you put stainless steel in a 16-inch and it's 1,200 feet deep, you don't have to go that deep. You're going to be up to $350,000 just in your casing. So, but the deal is the casing will last. If you're going to have with your carbon steel, you have to throw that out every 2.5 years and put new carbon in. So it was a lot more practical to put in stainless and let it run for 30 years versus jerking it out. You didn't have a choice. Okay, people, this is the cone of depression. When you pump a well, first of all, you have this is your water level. And as a well pumps, it's called cone of depression. So first of all, you have your static water level. Here's the water sitting down here somewhere in the ground. And then as soon as this well comes on, this starts to go like this. This is that void we talked about. Now the water is trying to run into that void because there's a void. And so it continues. Now the longer that well pumps, the larger this cone of depression starts. And it continues to do this. So with that said, you have to say, okay, if my cone of depression is too big, then I have to do something, because what happens is you start putting in wells. So you put in one well, but that well then starts to draw. The next well, number 2, if you don't space those properly, number 3 and number 4 well, they start drawing from each other. And so these cones of depression now, all of a sudden, this guy's drawing from him, he's drawing from him. When you set a well field up, you don't want overlapping cones of depression. You want one that is totally independent. This well is independent of that one, and you should not have any overlapping in your cones of depression. So you have to figure that all out. And you figure that out empirically, because you know what those wells do in that formation. Okay, here we go. So what you do then is how to properly develop a well field is you know what your production is. You'll notice these are larger and smaller wells. Some of them are 1,500, maybe one of them is 800 GPM well. And so then you say, okay, I need 7,000 gallons. How many wells is it going to take? Then you have to do a spatial relationship that this one's totally independent of this one. So they could be 5 miles apart, 2 miles apart, 3 miles apart. It's not just 10 feet or 15 feet. You're talking miles, because these cones of depression will be miles long as they start to extract that water. So you have to say, okay, where's this well, this well? And then also you need to know what the gradient is. Where's that water coming in from? Is it coming this way? Is it coming that way? Because you want to set those wells so that the gradient is up on top and that they're all receiving that water that way from the water flow. Okay? Coal-fired power plant, again, so I went through this scenario as far as we went from 10 wells to 19 wells. Here's the fun part about it. Okay, then what happened was I said, okay, look, every day you have to go out to the well field. You have to go find out what they're doing. How are they doing it? They shut down and so forth. We had a little bit of indication and a lot of indication. So there was this guy that was named Jay Norris. Jay Norris was out of Michigan. I needed some help. And so I just went to the internet. I was very blessed, people. You have no idea. Ever heard of Rumpelstiltskin? What happens with Rumpelstiltskin? As far as what happens with the straw? Turn it to gold. So what happened? He would give him the gold, and Rumpelstiltskin would turn the straw into gold, right? Well, this is how that Jay Norris was. This guy could do things. He never acted like he was intelligent, smart, or anything else. He could do things that you cannot believe. So anyway, I got on the internet, called him, and I said, Jay, he came out, we met, and I said, let's look at this. I said, what I want to do, I want to automate the entire well field. Well, what does that mean, automate? That means that you know what every well's doing every time. You know where the drawdown is. You know how many gallons they're producing. You know everything that's going on. You can turn them on, turn them off, do anything you want to in your office. So here's your monitor, and you then are just taking all you do. It's all right there for you. So I said, Jay, this is what we need to do. Let's install the radio towers and the controls on each well. They had to be line of sight. People where we live, there's mountains and hills. So you had to have a line of sight. So we had to put in a lot of towers. So this tower could see this tower, and this tower could see that tower. And finally get it back 20 miles away back to the plant. So we did that, and then we said we need all PLCs because it has to be programmable. We need to work with them that way. So we got all the towers and everything in. Then each well had to rest for 48 hours. And you know, they had to do a cycle, and they had to produce a blend. Only one well field was going to produce 70%, and the other well field was going to produce 30%. So you have all these different things that you have to accommodate for. You have to be able to do this, 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 and this isn't even half of it. And then what you have to do, what we keyed on, and hopefully you'll catch this, what really happened, is all your wells pump into what they call a raw water reservoir. And you want to operate that between 14 feet and 16 feet. So you don't want any higher than 16, you want any lower than 14 feet. So then you set up this great program, people, that was unbelievable. So once we automated the entire well field, then we set this parameter and told every well, you have to come on at a certain time. You have to produce a certain amount because you have to produce a 70-30, so this reservoir can only see 70-30%. You have to keep it here within a 14, 16 feet because we don't want to lose water and we don't want to gain water. So here's all the parameters that we had to set up that these wells had to do. So all these little children that you have to do out there had to start working for you. You're going to come on now, or you're going to shut off, you're going to produce so much water you aren't. Who's familiar with a VFD? It's called a variable frequency drive. Does anybody know what a VFD is? A VFD is nothing more than a variable frequency drive. In other words, you have a motor, and then you have input, and let's say this runs from, let's say, again, let's just use 3,600 RPM. You can tell it to run at 1,400, and that 1,400 RPM is going to produce 800 GPM. When you kick it all the way up, it's going to produce 1,500 GPM. So what you have is you have these variable frequency drives on your pumps. That helped this scenario because now this well could turn this off a little bit more, or he could turn him on a little bit more. He could run it at 3,600, or he could run him down at 1,500, or whatever the case may be. So all this fantastic automation it was all there. So I'd get in there, I could look at my monitor, I know exactly what the well fields were, I could see the levels. It was just unbelievable. So those are things that were really fantastic for this particular situation. Now they said, give examples of things that you love. This was great. You guys have no idea as far as the evolution from nothing up until one of the highest as far as automated and functioning well field that there ever was. But anyway, it was fantastic. Now I'm going to take you one more deal and then we're through. Okay, I remember that this is how it was. I could look at this. I knew the drawdown. I knew the GPMs. I knew what the pump setting was. One thing you don't want to do is cavitate a pump. Maybe no one knows what cavitate a pump means. When your drawdown comes here and your pump is here, you never want this drawdown here of your wells, of your water in your aquifer to go this low. If you don't have any water coming into your pump, you blow up your pump. So anyway, I knew exactly where my pump setting was. I knew where the water level was. If I have ever had an issue here, I knew it long before that water level dropped down, so I had an issue. Everything was there, variable frequency drives. Okay, this is a fun thing. As an environmental engineer, I worked on a lot of different things, but I also did a lot of mechanical engineering, just because that's where we were in a power plant. So we had an opportunity to do a lot of different projects. So this is what happened. There's a third point heater. Remember I said the heat that's out there, that we want to put it back into the system. These big heaters, what they do is they have tubes running in them. So the steam that's generated then in turn never sees the other water that's out here. Because this water is cooling, these tubes have steam. So they're never ever interfaced as far as actual water to water, but they're cooling that, okay? So they said what we need is your assignment is I want you to take this, because these wear out after a while. You're plugging tubes all the time because they leak, and pretty soon you plug so many tubes in that huge vessel that it no longer functions as far as a cooling vessel. So then what you have to do is pretty soon they're no longer efficient, you have to jerk them out. Well, when they build a power plant, a coal-fired power plant, the life expectancy was 30 years. So when you put a great big vessel that weighs 80,000 pounds, you didn't think it ever going to come out because the coal-fired power plant was only going to last 30 years anyway. So what these guys did is this is your ground level. This is sitting up here 40 feet in the air. It's not really in the air, but it's 40 feet from the ground on this grading. And here's this vessel. Well, they put it so far back in there that they thought, how are you going to get these out? We had to cut out huge steam headers. We had to cut out this. We had to do that to even start to get this thing. So they said, get rid of that and put a brand new one in. And so that was the challenge. I had 2 weeks to do it because you have a shutdown. A shutdown means the whole plant comes down, you do all your maintenance, you do everything you can, and get ready in 2 weeks to bring the plant back up, okay? So then we said, okay, that's your assignment. Elder Whiting, get it done. You got 2 weeks to do it. Well, that takes a lot. So we said, okay, how are we going to do this? First of all, where the heater was sitting was reinforced, but everything around the heater was no longer reinforced on the ground because it couldn't hold that much weight if you moved the heater from its original place. So you had to then reinforce a path. You had this great big path that you had to take to get that heater out of there. Well, so what happened was, here's your pipes. Here's your pipes. This is the path that we were going to take in. Then what happened is we came to what we call a crane bay. A crane bay is an opening, and the opening, there's a huge crane that can come down and grab that big vessel and put it on a big truck and take it off the plant. But you had to get it to the crane bay. Then the crane bay only had a 45-foot opening. So then you're restricted because you're going to use 40 feet. You can't bring it all the way out here because the crane only sits this far in here. Does this make sense? In other words, your crane can make a pick here, but it can't make a pick there. So you have to move this vessel out far enough to make a pick. That's what we call a pick, is just lifting it. So anyway, so this is what happened. So then we said, okay, so we had to We actually build just 4x8 steel plates. We had to put those big plates down. We had to reinforce the entire floor because if that vessel comes across there, it'd go down. So we made half inch thick, 4 foot by 8 foot, and then all of those were under here so we could start moving that. We welded I-beams, the crane bay and so forth was an issue. We had to have scaffolding, people, right here because we had to push this thing out in here so we could make a pick. So now you had to build scaffolding that was certified so that that scaffolding would hold 80,000 pounds. This was huge. Then, so what we did is we said, like I said, the heater stuck way back there. Typically you use tuggers. What's a tugger? It's a pneumatic winch is all it is. So you use these big tuggers and you just start jerking on that big vessel just a little bit at a time and you finally try to get the thing out. We had to make movements and everything. So what happened was I said, okay, I've never done this before, no one else has ever done it, but we're going to use airbags. We're going to float this thing out of here. Oh, everybody thought, oh, sure you are. So anyway, so what we did is I said, okay, and I've never done it before either. So we built these shoes, and these shoes were going to go on this great big vessel. We put these airbags under here. I did the research. Everything should be fine. We've never done it, so I told the welders, build these shoes, put this on this vessel. We got one shot at it. We hope it's going to work. Oh, my word. So anyway, so we put those on there. You had hoses. You had 4 hoses coming out of here, 4 hoses, and you have a control. You have 4 hoses coming out of here. Well, anyway, so we finally got to that point, and we said, okay, look, this is, no one knew, and so I got on the controls. We had this huge compressor supplying the air, and so pretty soon, turned on the 4 controls. All of a sudden you hear this big old rumble, and that big old vessel comes off the ground about that far, just about a ½ inch. So it's sitting there in the air. So then we take 15 men, and we start moving this guy. And remember, this is 80,000 pounds. Maybe it's in the air, but don't put your hand in between some steel beam and that vessel. It's still 80,000 pounds and moving in that direction. So now we start walking this great big vessel, and we start doing this guy right here, walking it all the way down to here, to here, to here, to here. Underneath, you have to get to that scaffolding. So sure enough, that big old vessel came up in the air like it was supposed to. We had 15 men moving it, and literally it was floating in the air. We brought it over to here. We put it on the crane bay, got it over there and made the pick. That big truck moved that one out. The new one was there. We pulled the brand new one in, made another pick, took the shoes off of the old one, welded them onto the new one, and then put those airbags on again and walked that great big vessel right back where it was. Turned off the air, we're done. So anyway, there are some fun things out there, you guys, that's really neat. That's called thinking out of the box. And like I said, I've been there for years and years. It was probably 30 years at that time. There was another engineer who was with me. Anyway, when they have these old welders, guys who worked around welders, big old welders, and they're tough old guys and all that good stuff, right? They all manly, man, they spit on the floor, do all those manly things, right? But anyway, so what happens is when we got to this point, and it was the first time ever, they let out a yell like, yeah! So anyway, it was a neat thing. This one engineer said, I've never seen anything like that. I've been here 30 years. As far as just the enthusiasm that went along with the deal. So anyway, just as far as things that are going on out there in the world and the opportunities it make, education was a fantastic situation. My biology degree was a stepping stone only. My master's degree is what opened it up for me. I never left that plant for 36.5 years, but it opened doors that never would have had that opportunity. Like I said, no one knew what I did. No one knew how I got the water there. Of course, they knew there's wells and stuff. No one knew how they built. They gave me a lot of money, people. I was project manager over millions of dollars of projects all the time. But it's because you gain the confidence, because you gain what you need to know as you develop these things. And so they trust you. So if you have the element of trust and you have the ambition, you think outside the box, and you can prove that your ambitions and your outside the box works, then people, it's a fun situation. So those are some things that are out there for you. You're in college students, look at some things. Be excited about your education, be excited about what you're doing, because it will open doors if you allow it to, and you just find out what those doors need to be and how you need to open them. So I leave you that, but anyway, thank you so much.
So I have a quick question about aquifers. So,
Okay, great.
I remember just in like middle school, I lived in Kansas, and my history teacher was going on and on and on about how the aquifer was depleting and how it was a big, huge problem. I mean, like, we hear about these aquifers emptying, but what happens when they are emptying? Like, what do we do about it? How is it fixed? Do we just leave the aquifer alone, or?
Well, that's a real good question. What happens, again, is recharge. Recharge, again, is the amount coming in to an aquifer. And if your recharge, again, is not sufficient, then you're going to have what they call overdraft. And overdraft means the same thing, basically. Your recharge and your extraction, your recharge is less than what you're taking out, you're depleting the aquifer. How do you, like you said, there's no other way to actually recover the aquifer unless you stop that and allow that. And again, it takes a long time for this aquifer to come back because, again, it has a lot of restraints. It's running through a formation. And again, depending on the formation, how fast is that water going to travel. Sometimes it travels just a few feet in a year. So it's hard. So people throughout the world right now, water is a huge issue. You want to go into environmental law? Go to water litigation. I mean, that's going on all the time. And so your point's very well taken. And again, when you have cities and so forth, and they come in and they start drawing on this aquifer, just like at the plant, everybody said 10 wells would be sufficient and you never have to worry about it again. Well, we ended up with 19, and we're still barely making enough water with a little bit of spare. So no one projects, I shouldn't say no one, but people do not project and look at the capacity versus what they're using. So you do have that situation where you have a real problem. And here you have this big city that's dependent on this water, and now you don't have the means or the ability to produce that water. So they do start looking at it, and it becomes very, very critical. But there's no real fix. The only fix is nature, and the only fix is the ability to transmit that water into here at a rate that's greater than it's being extracted, and then you're going to have to, everybody has to go to rationing or some other means to let that aquifer recover. That's about all. That's really the only solution you have when you start talking about depletion of aquifers, is you have to curtail that amount. Any other questions?
Well, okay, so we're talking about aquifers, and I've been abroad for the last 6 years, and I know this system's expensive, but where I was living, they had a program where they could draw water directly from the sea and change it into drinking water. How much time would that take? Is it viable? And where should people in Hawaii try to do something like that?
Well, that's a really good question. You do that when you have to. In other words, like you said, when you take desalination, that's what you're talking about, is you're taking all the salts and stinging out of water. And usually, there's a couple of means that do it. You can do it through distillation, or you can do it through ROs, which is nothing more than filters. RO. That's how you do it. Oh, the question is, desalination, again, state your question, and I'll...
So what I was saying is, where the city that I lived in for a while had a desalination program where they had several plants. I know it's expensive, so what I wanted to ask is it viable for people like
Here. Okay, no. Very good question. He's saying, why do we not, we have an ocean out there, desalination, why don't we use desalination? We have a huge ocean, let's go ahead and capture the water, I think is what he's saying. I mean, he did a very good question. But why aren't we? Well, number one, the reason is we don't have to. And number one, like you said, it's very expensive. When you start doing ROs, your ROs, you're going to get about 50%. So if you put in 100 gallons a minute, you probably are going to get out about 50 gallons. So 100 other 50 gallons has to be used and it has to be thrown away because you're concentrating the salts. So this salt that you're trying to get rid of is being through a filter, and you actually become just a slush, and that's what you're doing. So it's very expensive, these RO filters. Like I said, the return is only about half. When you put half in, or excuse me, all of it in, you're going to get half of it out. So your point's well taken. So in those situations, they say we have to. We don't have any choice. So they then say, okay, look, we know it's a terrible thing as far as the money associated with it, but we have to do it, so there's no other way that we can survive without going through desalination. Does that help it that way? And that's why they don't hear, because you don't have to. Greatest water in the world, cleanest water in the world, all the quantity that you want. So this particular situation where we are is, it wouldn't merit anything like that other than experimentation. So if somebody wants to do the research and so forth, they could set up a desalination and go that way, but there was no necessity based on need and consumption. Make sense? Okay, people, thank you so, oh, excuse me, one more.
You're from Arizona.
Arizona,
What part?
Northeast, St. John's.
So you have some male relatives who used to have a gas station chain?
That was my grandfather and my dad.
Okay. My mother grew up with them.
Oh, did you really?
Yeah.
Yeah, no, it's fantastic. So yes. But yes, so yes, that takes us right back. But yes, Arizona, yes, that's where we were. Okay, people, thank you so much. It's been very great. Thank you so much for the opportunity and appreciate being here.